All right, guys, here we go. We are going to start on our part 2 of chapter 1. So the first part of this chapter was just looking at matter and how we classify it with mixtures, so we can wrap our brain around like the different bits that we're all seeing. So like there were mixtures and substances and elements and compounds and all that kind of great stuff. And now we are going to, oh yeah, that's right, we also did like atomic structure and the history of atomic structure and how we got to like believing what we do, and not really believing, but knowing what we know. And now we're going to dig into electrons. Why, you may ask? Well, because all of the chemical reactions that we're going to look at for the rest of the year and for the rest of your life and for like forever, chemical reactions are basically electrons being shuffled around. And so electrons are really the part of the atom that are doing like all the chemistry, right? So if we're looking at chemistry, we're looking at we're really looking at what the electrons are doing, really. And also, electrons are super trippy. So it takes a little bit to, you can't be like, oh, there's an electron. You can't just look at it, because you literally just can't look at electrons. That you can't. It's not like you can't, like you physically literally can't look at them. So they are pretty trippy, and they're also like the thing that does all of the chemistry. So we're going to learn a little bit about electrons for the second half of this chapter. Okay. So first half was like stuff and atomic structure, and now we're going to specifically dig into electrons because they're weird, man. And so here's the thing: we quite literally cannot talk about electrons without talking about light. Here's kind of the thing. How do we look at things? Like, here's something worth looking at. Ah, beautiful cup of coffee. All right, let's just look at the mug. So if I set the mug over there, or no, here, look at my bow tie. You guys all look at my bow tie. Seeing the bow tie? Right. So how do you see the bow tie? Well, here's basically how it works. Light comes from an outside source. It collides with the bow tie and it bounces off. Right? It goes like the light goes off in all directions. Now this light's going off, and then like pretend the camera is your eyeball, and then it goes off and hits your eyeball, and your eyeball's like, woo, I see an image. And that's how it sees an image, from light bouncing off of things, right? Well, here's a problem with electrons. They're so super teeny that like when a photon of light hits an electron, it changes the electron. So it doesn't necessarily just bounce off. Sometimes it just passes right through and can't even interact with the electron. Sometimes it's absorbed. It's really weird. Sometimes light passes, sometimes light interacts, but if light does interact, it changes the electron, so it doesn't bounce right off because the electron is too small. So we never make what we call direct observations of electrons. Like when you look at my bow tie, you're looking right at it, bam, direct observation. We can't do that with electrons because electrons interact with light too much. So these are all indirect observations. And so because it's indirect observations, we need to understand a little bit about light before we can learn about electrons. Okay? So nothing complicated, but let's just dig into it. So light is called electromagnetic radiation. Man, if that's not a vocab term, I don't know what is. Give me a second. All right, I'm back. Sorry, like minor technical pen difficulties. See, I don't know what's going on there. So yeah, electromagnetic radiation. This is your new vocab word for today. Electromagnetic radiation. Yeah, basically, it's like the fancy term for light. That's really all it is. And light is basically energy, right? So light is energy that's carried by a particle. Now here's the deal: it has no mass, right? But super important, it has a specific amount of energy. Okay, and this little thing is called a photon. So light is this thing with no mass, which is good because it hits us at the speed of light, which would be really painful, but it does have energy. So no mass, but it does have energy. And this is really important to know, that a photon is a particle that has energy. Okay, but it doesn't have mass, so it's not really a particle. But it is a particle, but really it's just energy. So it's a particle and it's energy. It's both. It's both. It's both a particle and it's pure energy, kind of like all at the same time. And don't talk to me if that's weird. You have to talk to the universe. So What it is, it's like a pulsing field it's a pulsation in the electric field and in the magnetic field coming from a particle called a photon. Easy. But really, the only thing we need to know about photons are two things. First is the wavelength. Now, I don't know if you can really understand what wavelength might mean, but it's basically the length of this wave that the photon has, right? Because photons are so small that they do what's called wave motion, where they're they're basically pulsing as they go as they propagate through space, and the length of this wave, like a sine wave, like the up and the down thing, is just like the length of the wave, like you see right here, right? It's like it's like the distance between two equivalent points, or like two crests or two troughs, or like at right here it's like an up, so it's like near. Oh, there it is, right there. There's another up. So you see, these are all like the same distance. That distance, that distance, and that distance. They're all exactly the same. It's the length of a wave. And the other thing is frequency. Now frequency is weird. It is how frequently a wave passes. Because here's the thing about light. All light travels at exactly the same speed, no matter what. So all light is going the same speed. So if you have more waves go past you in like a moment, that means that it has a higher frequency because there are more waves passing you. So the frequency is the number of waves that pass a point, or like pass in front of your eyes, at a given amount of time. And for us, we use seconds because that's the base unit of time. And for some waves, you get a lot of waves per second. All right, so wavelength and frequency are best understood in comparison. Okay, and so let's look at two different waves in comparison. So remember, they are moving at exactly the same speed. So let's look at this guy. This dude starts here. It goes. This is an up spot. It goes. So this is one wavelength, right? So this here is one wavelength. Okay, now the other one here is the wavelength. So it starts here, it goes up, down, and there is its equivalent point. So can you see how the red wave has it's going to be a little bit longer. Actually, let me do this. Let me do this. I'm going to get rid of this. I'm going to go like this. This is going to be our red wave, okay? This is our red wave. And this is going to be our blue wave. Okay, you'll see why later. So if you look at this, the red wave has a longer wavelength. So if we just randomly took this and stopped it like right here, right at that time, right, this dude has a frequency of 1 because one wave has passed. The blue one has 1, 2. So there have been 2 of the blue waves for every one of the reds, so they're going the same speed. You get what I'm saying? It's just that the blue is like pulsing kind of faster, so it has more waves per second. And so if it has a longer wavelength, it's going to have a lower frequency, and a lower frequency gives us lower energy. Right? Does that make sense? Because it's got this really long, slow-moving wave. Because it's because the wave is stretched, not really slow moving, but it's all stretched out. And so since the wave is stretched out, you get fewer, it has a lower frequency or fewer cycles per second, which means lower energy. Okay? Now, in comparison, and that's sort of how everything is, it's like relative. You may have heard of relativity. Over here, our blue wave, right? It has a shorter wavelength, which gives it a much higher frequency. And because it has a higher frequency, that tells us that this photon has higher energy. Let's pretend that this is blue. All right, I'm going to change that someday. So that's the difference between wavelength and like long wavelength, short wavelength, low frequency, high frequency. This is really, and what I really want you to dial in here is this here, because this is like a nice correlation, that higher frequency means higher energy, and lower frequency means, just a second, lower frequency means lower energy. that is a really good relationship for us to hold on to, okay? Because that's really all we care about with light is like some is high energy, some is low energy. Every photon has a different kind of energy. That's really what's important for us, okay? What is important for, oh, look, there it is. It's like it's actually important for us that the energy of a photon depends on the frequency of the photon, right? So for us, we're going to correlate frequency to energy, being higher frequency means higher energy. Same thing, only opposite. Lower frequency means lower energy, right? It's easy. It's like very straightforward. The other thing that we should know is that every photon has a certain energy. When I say I put like unique frequency here. What I mean is like it has one frequency. So every photon, if you could like capture it, each photon has its own frequency. You may have two photons with the exact same frequency, but do you know what I mean? But so every photon has one frequency associated with it. It can only have one, right? So one photon, one frequency. That's all. That's what I'm trying to say there. I hope that makes more sense. And also, this is pretty trippy. All light's the same. It's exactly the same. Let me like even be a little more clear. All electromagnetic radiation is exactly the same. So when I pick up my cell phone, right, and I'm using my cell phone, the signal that it's using is light, but it's light that we can't see. It just goes through us, it goes through buildings, it goes through trees, just like light goes through windows, right? Like visible light can go through windows. Cell phone light can go through things, right? X-rays that we use to take X-rays and look through our bodies, it's the same exact stuff as light that we use to look at the world. Our eyes just aren't calibrated for X-rays, or the microwaves that our cell phones use. It's all the same thing. So the only difference between a photon of microwave light that your cell phone is using and a photon of blue light that we see is frequency, like the amount of energy that photon contains. And the only difference between that blue photon that we can see and X-rays that we use to look at our bones is the amount of energy or the frequency of that photon. It is all the exact same thing, just different energies. Okay? So that's kind of what I'm trying to say here. Like radio waves have very low energy. I can't remember the length, but like radio waves are long, like skyscraper long, like hundreds of meters long. And then this is fun. Microwaves, we use it to like heat up food and use our cell phone. So make sure that's pressed right up tight against your head. Infrared, this is fun. This is like a good way of transferring heat to molecules. This is why when you're outside in the middle of winter and you're having a bonfire, the front of you is like 1,000 million degrees because it's all that light. And by the way, it's infrared. It's light that our eyes can't see. But it hits our body and we get super duper warm. But our backside is not getting light, so it's like minus 30 degrees. And like our backside's frozen, our front side is boiling. It's because of infrared radiation or infrared light. We like to say infrared radiation because it's electromagnetic radiation. It's all the same thing. It's just light. And then we have this, and this actually to scale is not quite accurate. If you took the whole band, like visible light is about that wide. That's about how much visible light we have. Visible light, our eyes are calibrated to a very small range of electromagnetic radiation. They move into ultraviolet. That's the stuff that gives us like sunburns and stuff like that. X-rays, we know that. We all know what X-rays are and whatnot. And then there's gamma rays. Gamma rays are high energy radiation, often used for killing. We use it for killing, mostly sanitizing. We don't really like to use gamma radiation too much for killing cancer for other reasons that we'll talk about at the end of the year when we talk about nuclear chemistry. But for right now, I need you to know that it's all the same stuff. Okay. So now, what you need to know. Two things. I guess you need to know a lot more than two things, but let me dig into two specific things that I need you to know. One, I need you to really own, I need you to own this whole ball of wax right here, that all light is the same thing. They are photons. They are just of different energies. And then what I also need you guys to lock onto is this whole graphy chart right here. Well, that didn't work out too well for me. I shouldn't do two things at once. This whole graphy chart thing right here. So what this means is, I want you to remember Roy G. Biv, right? Would you bet? You take your elbow, drop it low. Would you bet? I wish you were here in person. It's so much fun. Anyway, you need to know. Would you bet? Red is low energy, orange, yellow, green, blue, indigo, violet. Very high energy for violet, like ultraviolet, sunburns. Red is very low energy, like infrared. You're just chilling. Like, how does that make you feel to sit in front of like a campfire or the wood stove? You just chill. It makes you relaxed. It's so toasty, so wonderful. So yeah, you need to know the order of the colors in terms of energy. Red, way low. Violet, way up high. If you're not sure, you take your elbow, you drop it low. Trust me, just do that one. Just do that. It works. All right, so that leaves us with a review of the wave mechanical model and how electrons behave inside of it when they interact with light. Here we go. Wave mechanical model. It's the modern model of the model. Modern model of the atom, but you already know that. Electrons occupy the area around the nucleus like a cloud. We already went over this, right? And that cloud is called orbitals. And we're going to refine this to orbitals are areas with a high probability of finding an electron because, you know, when an electron is inside that orbital, it stops being a particle and becomes like a probability cloud. Like it's probably somewhere inside that cloud. It's crazy quantum stuff because electrons are so small that they don't really behave what we call Newtonian physics, the kind of physics that you and I see, like when we throw a ball, or like, I don't know, when we walk into a wall. You know, for us to go from point A to point B, we have to move there. But in quantum mechanics, like, you just go from point B and then you appear or you go from point A and you appear in point B. You don't even have to move across space to do it. You just blink and there you are. Don't get me started. It's crazy. So these orbitals, here's all we need to know. They form energy levels like a set of ladders. They build, right? Or like the other analogy I use, like floors in a building, right? So the higher you are, the higher the higher energy you have. And the energy or the orbital that the electron is depends on the amount of energy. So the higher energy is the higher level. Right? Because like it's like we talked about potential energy. When you're on the 10th floor, you have a lot more gravitational potential energy than you do on the first floor. Same thing with electrons, and they're like electron potential energy. Yeah, let's go with that. If an electron is in a high energy level, that means it has a high electron potential energy. If it is in a low orbital, that means it has low electron potential energy. You guys dig what I'm saying? And now here's something that we talked about. This is like where Bohr almost had all of his stuff. Electrons can gain and lose energy and move up and down energies like climbing a ladder. And the kind of energy you can gain or lose or to do this is like pretty much anything. Light, heat, electricity, you name it, it can do it. However, we are going to stick mostly with light because that's just the easiest and kind of makes the most sense. And one type of energy is light. That's where we like to stay. And now I really want to dig into this. So when electrons lose energy, they give off light. And when we say give off, like we use a symbol like this. So that's like a wave for light, and that's an arrow saying it's going off. And they fall down to a lower energy level. So for electrons to give off energy, they need to go from high energy to low energy. Okay, that's how they give it off. And if they're going to absorb energy, it's the same thing, only backwards. They have to start at a lower energy, they absorb it, and then they end up at a higher orbital, at a higher energy orbital. Okay? Now, this is a trippy thing. Partial steps are not allowed. There is at no time does an electron exist between energy level 1 and energy level 2. It just pops. I can't remember what they call it. It's called like a quantum shift or something like that. It doesn't travel from point A to point B. It is at one moment in time at point A. The next moment in time, it is at point B. Go figure it out. It is what the quantum world is. The quantum world takes our human intuition and like throws it into the garbage can because, you know, we're humans and we understand things at this scale. We've never been the size of an electron, so nothing makes sense to it. It doesn't make sense, but there it is. But the analogy is very similar to climbing up a ladder. You cannot stand in between the rungs of a ladder. Why? Because there's nothing there to support you. So why can't electrons like exist in between energy level 1 and 2? Reason being is that electrons have a wave function, and there is no way that they can exist between energy levels because it's too unstable. There's nothing to hold them there. Very similar to us trying to stand in between the rungs of a ladder. There's nothing there. It doesn't happen. You don't stand in between the rungs of a ladder. Electrons don't exist between energy levels. That's it. There is no in between here. Up, it's like energy level 1, it's energy level 2, energy level 3. Got it? Got it. And here's the thing. Electrons do everything they can to get back to the ground state, always. So here's how here's how it works. Energy goes in, the electron goes from the ground state, or where it normally is, its lowest energy state, it pops up here to the excited state. All right? But just like throwing like an egg up in the air, it falls right back down. So it goes from the excited state down to the ground state, and that is when energy goes out. This is how a black light works. So the way a black light works is first you have like your black light, right? And it's giving off black light. It's really just light that our eyes are not calibrated with, okay? So that black light hits certain molecules, certain electrons, and those electrons go from a low energy, they absorb that light, and they go to an excited state. They go from the ground state to the excited state. Well, just like everything in the whole wide world, when it goes from the excited state and it's like way up high, it falls back down. So what it does is when it goes from the excited state back down to the ground state, it has lost a little bit of energy. How is that possible? Well, you've moved the electrons around, so you've done work. And it's sort of like the sun heating up a black leather seat in the summer. It absorbs solar energy. And so the light that comes out, right, this new photon that comes out is a color that our eyes can see. So the light going in is a color that we can't see, but the light going out has been changed just enough so our eyes can see it. Pretty trippy. I bet you never knew that you were looking at like electron excitation and relaxation from ground to excited, excited to ground. There's a lot of chemistry going on there. So here's the thing. So what? So it gives us atomic emission spectra. That's what. And you might be asking, what are atomic emission spectra? Well, let's look at the words and see what words mean, because that's why we have words. Atomic means atoms. What does emissions mean? Like, what are emissions? It just means spitting out. And what, pray tell, does the word spectra mean? Well, that's like fancy science word for rainbows, because we can't say like we're looking at rainbows, because then people don't think we're being sciencey and fancy, but it means rainbows. So atomic emission spectra really means atoms spitting out rainbows. Atoms spitting out rainbows. That is what that means. It's true, because if you take atoms and you zap them with energy, they spit out rainbows. So here's the deal. When energy, like electricity, is applied to atoms, they will emit light to release some of that energy. Like fluorescent lights or like a neon light. That's a really good example, right? So what happens... Oh man, that's the bell. Hey guys, I gotta peace out. I'll be back in a little bit. Okay, stay tuned. Okay, so what do we call these things? These atomic emission spectra? We call them atomic emission spectrum, right? Or like quite literally, we call them like atoms spitting out electrons. Whoa, that's not what I wanted to do. Hold on. We call them atoms spitting out electrons. And so here's the thing. This is why it's really good or like useful for us, is because every element has an absolutely unique like spectrum. It works exactly like a fingerprint, because every element has its own set of protons, right? Because the number of protons identifies the element, and therefore it has the exact same number of electrons, because you need for every one proton you need one electron. So because each element has a different number of electrons, right? Like all the carbons have 12 electrons, like all of them. I think all of the... Wait, is it 12? Hold on, let me look. No, I'm totally wrong. Carbon has 6 protons, therefore 6 electrons. Oxygen has, hold on, has 8. I'm looking at the periodic table because I obviously don't remember anything. So carbon has 6, oxygen has 8 electrons. That means that carbon and oxygen are going to have a different atomic emission spectra because there's a different number of electrons bouncing around and doing weird electron things. And so we can use this to identify elements. That's how we know when we look at the sun, that like what the sun is made of. We just like put the light through a prism and we just look at it. And you know, because each element has its unique spectrum, we just look at the spectrums. What matches up here on Earth matches the sun too. It's quite nice. Oh, but here's the deal. When we take our elements and we zap them with electricity and they glow and they spit out their atomic emission spectra, we only see one light. You know what I mean? Like you look at the sun, you see like one color of light. However, if you put that light through a spectrum, it breaks it apart and we see lots of different colors. Even with the sun, like we see rainbows, right? But if we took a rainbow and put that rainbow through a spectrum and then that through a spectrum, you're going to start seeing those same individual like lines instead of a broad spectrum of every single color, because electrons are going from excited down to ground and giving off a single packet of light. In other words, it is not one continuous flow of energy. There are limits. There's like they separate, and that's where the word quantum and quantum physics come from. Quantum means quantity. In other words, energy comes in quantities. Trippy, isn't it? But anyway, going back to elements, you take an element, zap electricity, like the electrons are excited, and then they fall back down to ground. They go to the excited state, down to ground state, the excited state, back down to ground state. We take that light, like the glowing atoms. You put it through a spectrum, and instead of getting a big broad rainbow, we get individual lines. And every element, those lines are absolutely unique. And we can use that to identify an element. Got it? Excellent. Now, usually when we do this, we get a bunch of different lines. And the question is always, well, how do we get so many lines? Hear me explaining it to you. All right, so let's do red for an electron. Let's say we have an electron in level 1. We put that electron into what do you want to put that into? I don't know, a light bulb or something. Like, let's say we have a neon light. You switch it on, and neon lights usually have like 5,000 volts of potential difference. That's a lot of potential difference. Bam! We smash this electron. Whoa, where'd the electron go? There it is. We take this electron, we smash it all the way up to the energy level 6. Now, here's the deal. Why are they disappearing on me? I don't know. So if we have something in energy level 6, it could... That's so strange. I don't know why it's doing that. Because, you know, why wouldn't it? Give me a quick second here, guys. I'm going to see if I can. Maybe. Who knows if this will work. But where I left off is I was using a pen, and it was red, and we had an electron way up here in energy level 6. Now, the deal is, it's going to fall down, right? Because as soon as you get to the excited state, it's going to fall down. So as it goes from energy level 6, it could go boop, to energy level 5. And that'll give you 1 emission. It can also go from 5 to 4. And then, boop, that'll give you a 2nd emission. It can go from 4 to 3. And then, boop, there's another emission. It can go from 3 to 2. And then, boop, that is another emission. And then 2, finally back down to 1. And that is your final emission. But that's not all, right? That's not the only sequence. If it's at number 6, it could fall down to 4. And that gives off another one. It could go from 6 all the way down to 2. And that's yet a different one. So you can see how, like, you can start getting lots and lots of different lines. And all those lines, like, they hit our eyes all at the same time, and our eyes see only one color. Not like they see that, not like just one photon at a time, because that's not how our eyes work. Anyway, this is kind of what it looks like. And these are the questions that we ask, is what is this unknown element here? And so if we take this element, the unknown, and we put it in an energy source and we zap it and it starts to glow, we take that glowing light, we put it through a spectrum, and we get all these different lines here, right? You see we've got like a purple, we've got like a triplet blue, we've got orange, we've got red, and I don't even know what color that is, but it's some kind of reddish on the edge of our visible spectrum there. So there's our unknown. And we just literally compare it to all the other ones. The only difference is now we use computers instead of like physically trying to like compare these. And so whatever the element it is, it has to have all of these lines and no additional ones. So all we do is line them up and compare. Could it possibly be beryllium? Well, beryllium's got this purpley do right here. So beryllium's out because I don't see a purpley do right there. I do see a pretty good match right here, but this, like, no, it has to be an exact perfect match. Just like fingerprint has to be an exact perfect match. Move on. Copper. Then just no, like absolutely not. There's no way, because there's nothing, like that's not even, that's like no. Could it be manganese? Well, there's a, no. See, it doesn't match. Let's go to strontium. It's got, well, it's got this one. Oh, that matches up pretty good there, doesn't it? And look at this triplet. Like 2 that are close and 2 that are far. 2 that are close, 2 that are far. Nada, nada, nada. There's, oh, that's squiggly. There's your orange. Whoa, dude. I can do this. I can draw a straight line. There's your red. There's your, I don't know what color that is. It's right there. Here, I'm gonna go like that. See how this has like a weird like color? I don't know what color that is. Rust. There it is. So it's got to be strontium. It absolutely must be strontium, because strontium matches perfectly. And then we're going to rule out titanium as well, because, well, none of those colors match. Does it make sense? So the unknown has to be strontium, because the atomic emission spectra are exactly alike. You dig what I'm saying? Do you guys dig what I'm saying? See, they understand. So should you. It's pretty straightforward. It's not terribly complicated. What the electrons are actually doing and why. That's like so complicated. But for a chemist working in a lab, all we care about, you take your element, you zap it with energy. The electrons go from the ground state, which is the lowest state where it's normally found. They absorb some of that energy to a higher state, what we call the excited state. And just like jumping up in the air, when you're excited, as soon as you're up there, you fall right back down. And that's exactly what electrons do. And when they fall down, they spit out energy. And it's usually in the form of light. And that light can be put through a spectrum, and it makes these lines, right? Instead of a continuous rainbow. And those lines can be used to identify the element. You guys picking up what I'm putting down? We don't need to worry about the quantum jumping from energy level 1 or energy level 2. If you want to dig into that, go into like particle physics and stuff like that. Because that, oh, that's nice. See, this makes me happy. Because we're done, or at least I'm done. Now it's you guys, it's your time to start working. 2 things that we're going to work on next are shedding light on light. This is a true-false thing, where some of them are false, and then you need to make it true. So you really actually need to know your stuff. And don't forget, you can do these with your notes, like right next to you. When we're done that, we are going to look at the Bohr model versus the wave mechanical model, because Mr. Bohr got a lot of things right, which is amazing, because like, back in the day, like they didn't even have a computer. They did everything. It's incredible what this man was able to do. Probably let me put it to you this way. What Bohr discovered and figured out was like Einstein was like, that can't possibly be, and he basically outsmarted Einstein. So Bohr, smart. So we're gonna, but he almost got it right. So we're gonna compare the Bohr model versus the wave mechanical, or what we call the modern model. That's it. I hope it doesn't break your brain too hard. Look forward to seeing you tomorrow. Have a great day.